Welcome to our presentation on stress transformation, part of the FMB 20303 Strength of Materials course. Today, we'll be exploring how stress transformation plays a crucial role in understanding material behavior under different loads and conditions. We'll also dive into its practical applications in engineering, from structural design to aerospace engineering. Let's get started. Now, let's introduce the team presenting today. We are Group 5, and the members are 1. Asbullah bin Abdul Aziz, 2. Muhammad Shafiq bin Muhammad, 3. Muhammad Noor Azmi bin Muhammad Noordin, 4. Mohd Ifai Akmal bin Ibrahim. We'll be guiding you through the concept of stress transformation in this presentation. In this introduction to stress transformation, we'll be focusing on how we determine the state of stress at any point in a material. This is done by analyzing the normal and shear stresses on different planes. Stress transformation helps us understand how forces are distributed across materials when they are subjected to various load conditions, which is essential for predicting material behavior and ensuring structural integrity. Now, let's dive into the two main stress components involved in stress transformation: normal stress, sigma. This is the stress component that acts perpendicular to a given surface. It plays a key role in how a material deforms when subjected to external forces. Shear stress, tau. This component acts parallel to a given surface, causing material layers to slide over one another. Shear stress is essential in understanding how forces affect material strength and stability. Now, let's explore why stress transformation is so important. Stress transformation allows us to identify critical stress components, helping predict material failure or deformation. By understanding these components, we can avoid material failure in real-world applications. This technique is vital across various fields, including engineering structures, materials science, and mechanical design. It helps ensure the integrity and safety of products and structures under different load conditions. Next, let's talk about plane stress transformation. Plane stress occurs when the material is subjected to stresses in only two dimensions. This is commonly used for thin sheets or plates under loading conditions. In this case, the third dimension is either not subjected to stress or has negligible stress compared to the other two dimensions. Understanding plane stress is essential for analyzing thin structures, ensuring their strength and integrity under different loads. Now, let's look at the equations used in plane stress transformation. These transformation equations allow us to calculate normal and shear stresses on any plane of interest. The general transformation of stresses is described by the following equations, where the transformed stresses correspond to a new orientation of the plane. These equations are crucial for understanding how stress components change as the plane orientation changes, helping us analyze materials more accurately. In plane stress transformation, we deal with three key stress components. Sigma. This is the normal stress in the x direction. S. This is the normal stress in the y direction. Tau. This is the shear stress acting on the plane. These components are critical in understanding how the material behaves when subjected to stresses along different directions. In this slide, we see the transformation equations for the plane stress problem. These equations are used to calculate the normal and shear stresses at a new orientation of the plane. The equation for normal stress in the x direction, sigma, is a combination of the normal stresses in the x and y directions, along with the shear stress, all rotated by an angle theta. Similarly, normal stress in the y direction, S, is calculated using the same principles. The shear stress, tau, is also affected by the rotation of the plane and is calculated using this transformation, where theta represents the angle of rotation of the plane. These equations are key for transforming the stresses from one orientation to another, enabling a more detailed analysis of material behavior under different loading conditions. The general equation of plane stress transformation is an essential aspect of the stress transformation process. It utilizes the transformation equations to express normal and shear stresses on a plane at an angle theta. This equation is derived from the previous equations we've discussed, which consider the normal and shear stresses in the x and y directions. Using this general form, we can calculate the stresses at any plane orientation, allowing for a more precise and flexible analysis of materials under different stress conditions. This is the general equation of plane stress transformation in matrix form. It expresses the transformed stresses on a plane at an angle theta. The matrix shows how the normal and shear stresses in the x and y directions are transformed into the new coordinate system. The terms involving cos squared theta and sin squared theta relate to the rotation of the plane, while the shear stress tau is also affected by the rotation. This equation provides a comprehensive way to calculate the transformed stresses at any orientation, which is essential for detailed material and structural analysis. Now, let's look at principal stresses and the maximum in plane shear stress. Principal stresses are the maximum and minimum normal stresses in a material, occurring on planes where the shear stress is zero. These stresses are crucial for understanding the material's potential for failure. The equations shown here allow us to calculate these principal stresses sigma and sigma. They are derived from the normal stresses in the x and y directions, as well as the shear stress. These calculations are essential for determining the critical stress points within a material, especially in failure analysis. Next, we have the maximum in plane shear stress, tau_max. The maximum shear stress is the difference between the two principal stresses, sigma and sigma, divided by 2. This is a key factor in understanding how materials behave under stress, especially in failure analysis, where maximum shear stress indicates areas that might experience sliding or deformation. Now, let's talk about the principal plane, which is the orientation of the planes that carry the principal stresses. These planes are at an angle theta from the original x and y axes. The angle theta can be calculated using the equation shown here, which involves the shear stress tau and the normal stresses sigma and s. This angle helps determine the orientation at which the principal stresses occur, which is essential for understanding how the material will behave under the applied loads. Next, we'll discuss Moore's circle for plane stress. Moore's circle is a powerful graphical tool that helps visualize the transformation of stresses. It allows us to see how normal and shear stresses change on different planes and helps determine the principal stresses as well as the maximum shear stress. This method is widely used for stress analysis because it offers a clear, intuitive way to understand complex stress states. Let's now go through the steps to draw Moore's circle. 1. Plot the given stresses. Start by plotting the stresses sigma, s, and tau on a graph. The x-axis will represent normal stress, while the y-axis will represent shear stress. 2. Draw the circle. Using the principal stresses and shear stresses, draw the Moore's circle. 3. Use the circle to determine O the principal stresses, sigma and sigma. O the maximum shear stress, tau_max. O the orientation of the principal planes. Moore's circle provides a visual way to easily analyze these critical stress components. Here is an example of Moore's circle for plane stress. As we can see in the graph, the circle represents the transformed stresses, with the x-axis showing the normal stress and the y-axis showing the shear stress. The points on the circle correspond to different planes of interest. By using the circle, we can easily determine the principal stresses and the maximum shear stress, as well as the orientation of the principal planes. This visualization helps in quickly analyzing the stress state of materials under various loading conditions. Now, let's focus on the center and radius of Moore's circle. The center of the circle is calculated as the average of the normal stresses in the x and y directions. This is given by the formula center of the circle equals sigma plus s, 2. The radius of the circle is calculated using the difference between the normal stresses, along with the shear stress. The formula for the radius is radius of the circle equals square root sigma s squared 4 plus tau squared. The center and radius are essential for accurately plotting Moore's circle and determining the principal stresses and maximum shear stress. Now, let's go through an example of Moore's circle for plane stress. Let's say we have the following stresses. Sigma equals 50 megapascals, normal stress in the x direction. S equals 30 megapascals, normal stress in the y direction. Tau equals 20 megapascals, shear stress. These values will be used to plot Moore's circle and calculate the principal stresses and maximum shear stress. Now, let's calculate the principal stresses using the formulas for sigma and sigma. Given the normal and shear stresses, sigma equals 50 megapascals, S equals 30 megapascals, tau equals 20 megapascals, we can apply the formulas. For sigma, the maximum principal stress, and for sigma, the minimum principal stress. These principal stresses are critical for analyzing material failure and behavior under different load conditions. Now, let's calculate the maximum shear stress, tau_max. Using the principal stresses sigma equals 62.36 megapascals and sigma equals minus 17.64 megapascals, we can apply the formula. This value represents the maximum shear stress, which is an important indicator of potential material failure due to shear forces. Let's now calculate the center and radius of Moore's circle. The center, C, is the average of the normal stresses sigma and S. The radius, r, is calculated using the difference between the normal stresses and the shear stress. These values are essential for plotting the Moore's circle and finding the principal stresses and maximum shear stress. Here is the Moore's circle for plane stress with the calculated values. As shown in the graph, the center of the circle is at 40 megapascals. The radius is 22.36 megapascals. The red points on the circle represent the normal stresses, while the shear stress is represented along the y-axis. From this graphical representation, we can easily determine the principal stresses, maximum shear stress, and the orientation of the principal planes. Let's now look at a case study on bridge design. In this case, engineers are designing a suspension bridge and need to calculate the stresses acting on various components of the bridge, especially during high wind loads or heavy traffic. Stress transformation. By using stress transformation equations, engineers can calculate how the stresses are distributed across different parts of the bridge, including beams, cables, and pillars. Outcome: this transformed stress data helps engineers identify high stress areas, allowing them to reinforce those areas, thereby ensuring the bridge's safety and structural integrity under different loading conditions. Now, let's move on to the question for the bridge design case study. We are given a bridge beam subjected to a bending load, and we are provided with the following stresses. Normal stress in the x direction, sigma, equals 100 megapascals. Normal stress in the y direction, S, equals 50 megapascals. Shear stress, tau, equals 30 megapascals. These values will help us calculate the principal stresses and maximum shear stress using stress transformation techniques. Let's calculate the principal stresses, sigma and sigma, for the bridge beam. Given the normal stresses, sigma equals 100 megapascals, normal stress in the x direction, S equals 50 megapascals, normal stress in the y direction, tau equals 30 megapascals, shear stress. We use the principal stress formulas. Thus, the principal stresses are, sigma equals 113.73 megapascals. Sigma equals 26.36 megapascals. These principal stresses are crucial for understanding how the beam will behave under the applied bending load. Next, let's calculate the maximum shear stress, tau_max, for the bridge beam. Substituting the principal stresses we calculated earlier, sigma equals 113.73 megapascals. Sigma equals 26.36 megapascals. This maximum shear stress indicates the greatest amount of shear the material will experience, helping engineers assess potential failure or deformation. Let's now look at case study 2, aircraft wings. Situation: aircraft wings experience high loads due to air pressure and aerodynamic forces. Since the material of the wing is thin, plane stress transformation is used to calculate the stresses. Stress transformation. Engineers apply stress transformation to determine the shear and normal stresses on different sections of the wing as it undergoes various aerodynamic loads. Outcome: by accurately calculating stresses on different planes, engineers can optimize the material and design of the wing to ensure its safety without adding excessive weight. Now, let's look at the question for the aircraft wing case study. We are given the following stresses on an aircraft wing subjected to aerodynamic forces. Normal stress in the x direction, sigma, equals 80 megapascals. Normal stress in the y direction, S, equals 40 megapascals. Shear stress, tau, equals 50 megapascals. These values will be used to calculate the principal stresses and maximum shear stress using stress transformation techniques. Let's now calculate the principal stresses, sigma and sigma, for the aircraft wing. Given the stresses, sigma equals 80 megapascals, normal stress in the x direction, S equals 40 megapascals, normal stress in the y direction, tau equals 50 megapascals, shear stress. We use the principal stress formulas. Thus, the principal stresses are sigma equals 112.43 megapascals. Sigma equals 7.52 megapascals. These principal stresses help us understand how the wing will perform under the applied aerodynamic forces. Now, let's calculate the maximum shear stress, tau_max, for the aircraft wing. Substituting the principal stresses we calculated earlier, sigma equals 112.43 megapascals. Sigma equals 7.52 megapascals. This maximum shear stress is important for assessing potential shear failure in the aircraft wing material. Let's move on to case study 3, pressure vessel design. Situation: a company is designing a high-pressure vessel for storing natural gas. The vessel is subjected to both internal pressure and external forces, which can cause stress on the vessel walls. Stress transformation. Engineers use stress transformation equations to calculate the stresses at various points on the vessel's walls. These calculations help determine the principal stresses and ensure that the vessel can safely withstand the pressure fluctuations. Outcome: by analyzing the transformed stresses, engineers can identify weak points in the vessel and apply appropriate reinforcements, ensuring that the vessel remains safe and avoids failure due to pressure fluctuations. Now, let's move on to the question for the pressure vessel case study. We are given the following stresses on a pressure vessel. Sigma, normal stress in the x direction, equals 40 megapascals. S, normal stress in the y direction, equals 20 megapascals. Tau, shear stress, equals 30 megapascals. These values will be used to calculate the principal stresses and maximum shear stress in the pressure vessel to ensure its safety under the applied internal and external forces. Let's now calculate the principal stresses, sigma and sigma, for the pressure vessel. Given the following stresses, sigma equals 40 megapascals, normal stress in the x direction, S equals 20 megapascals, normal stress in the y direction, tau equals 30 megapascals, shear stress. We use the principal stress formulas. Thus, the principal stresses are sigma equals 61.62 megapascals. Sigma equals minus 1.62 megapascals. These values help us understand the stress distribution within the vessel, which is essential for its structural integrity under pressure. Now, let's calculate the maximum shear stress, tau_max, for the pressure vessel. Substituting the principal stresses we calculated earlier, sigma equals 61.62 megapascals. Sigma equals minus 1.62 megapascals. This maximum shear stress helps determine the potential areas for shear failure in the pressure vessel. Let's now look at case study 4, beam under bending. Situation: a structural engineer is analyzing a beam subjected to a bending moment in a building's framework. The bending stresses are critical to ensuring the beam's strength. Stress transformation. The stress transformation equations are used to calculate how the bending stress is distributed along the beam, taking into account its length and support conditions. Outcome: engineers use this information to ensure the beam's material and dimensions are sufficient to resist bending stresses without causing permanent deformation. Let's now look at the question for the beam under bending case study. We are given a beam subjected to a bending moment of 100 kN, and the beam has the following properties. Length equals 5 meters. Cross-sectional area equals 250 square millimeters. Moment of inertia equals 3,500 centimeters to the power of 4. Young's modulus equals 200 gigapascals. Using these values, we can calculate the bending stress distributed along the beam, considering its dimensions and support conditions. Now, let's calculate the bending stress, sigma, for the beam. Where m is the bending moment, y is the distance from the neutral axis, I is the moment of inertia. We will use this formula to determine the stress distribution along the beam, ensuring it is capable of withstanding the applied bending moment. Let's now calculate the bending stress, sigma, for the beam, using the formula we discussed earlier. We are given the following values. M equals 100 kN equals 100 times 10 cubed Nm. Bending moment. I equals 3,500 centimeters to the power of 4 equals 3,500 times 10 to the power of 8 m to the power of 4. Moment of inertia. Y equals 0.25 meters. Distance from the neutral axis. Assuming the height of the beam is 0.5 meters. Now, applying the formula for bending stress. This bending stress calculation helps us ensure that the beam's material and dimensions are adequate to resist the applied load without permanent deformation. Let's now look at case study 5, fatigue crack propagation in a rotor blade. Situation: an aerospace company is analyzing the rotor blades of a helicopter to prevent fatigue cracks from propagating, which could lead to failure over time. Stress transformation. Moore's circle is used to calculate the transformed stresses on the blade surface under cyclic loading. This helps engineers identify areas of maximum shear stress, which are most susceptible to fatigue failure. Outcome: the analysis helps refine the rotor blade's design by reinforcing areas prone to fatigue failure, ultimately extending the blade's lifespan and improving the helicopter's safety and reliability. Now, let's look at the question for the rotor blade case study. The rotor blade experiences cyclic loading with the following stresses. Normal stress in the x direction, sigma, equals 150 megapascals. Normal stress in the y direction, s, equals 50 megapascals. Shear stress, tau, equals 75 megapascals. These stresses will be used to analyze the transformed stresses and identify areas of potential fatigue failure using Moore's circle. Let's now calculate the principal stresses, sigma and sigma, for the rotor blade. Given the following stresses, sigma equals 150 megapascals, normal stress in the x direction, s equals 50 megapascals, normal stress in the y direction, tau equals 75 megapascals, shear stress. We use the principal stress formulas. Thus, the principal stresses are sigma equals 190.13 megapascals. Sigma equals 10.87 megapascals. These values are essential in determining the critical stress points in the rotor blade for fatigue analysis. Now, let's calculate the maximum shear stress, tau_max, for the rotor blade. Substituting the principal stresses we calculated earlier, sigma equals 190.14 megapascals. Sigma equals 10.87 megapascals. This maximum shear stress is crucial for determining areas where fatigue cracks are likely to form, helping engineers reinforce those regions to avoid failure. Here is Moore's circle for rotor blade stress. This Moore's circle graph shows the transformed stresses for the rotor blade. The red points on the circle represent the normal stresses sigma and s, while the shear stress is represented along the y-axis. From this circle, we can easily identify the principal stresses and the maximum shear stress for the rotor blade. Using Moore's circle allows engineers to quickly analyze areas of the blade that are prone to fatigue failure, optimizing the blade's design for safety and durability. Conclusion: stress transformation is a vital tool in engineering and material science. By applying stress transformation equations, engineers can calculate stresses at any point within a material, considering different orientations or loading conditions. Identify principal stresses and maximum shear stresses, which are crucial for understanding where materials are most likely to fail. Optimize material design by reinforcing high stress areas and ensuring that structures can withstand various loading conditions, whether from external forces, internal pressure, or cyclic loading. In summary, stress transformation enables engineers to design safer, more efficient structures by understanding and mitigating stress-related failures. In structural engineering, mechanical design, and aerospace engineering, stress transformation plays a crucial role in creating safer, more efficient designs. By applying stress transformation equations, engineers ensure that materials and structures can perform optimally under real-world conditions. Using tools like Moore's circle and the transformation equations, engineers can better predict and prevent